tiny. Small tiny. But I will start. We have second lecture today.
Shame on you. No, if I didn't, how would their school probably be messy?
Yes. Let's go. Now, let's say I have a periodic signal where m is an integer. I have a periodic signal. I would like to perform a Fourier transform on this signal. I would like to get ideal components of this signal. Let's start from C1. Cosine factor of the first harmonic base frequency. C1 will be 2 divided by integrating from 0 cosine double P
Correct? Yes, correct. Let's assume that I do have a values of my signal. I have stable of my signal where is t divided by n. I have n values in one period, and I change from 1. I have something like this table. Number 1, 2, 3, 4. Value of signal. I don't know. Volts. But I do have a signal table. Table of my signal values. Time. I don't know, maybe like this. This is one period, and this one is cosine of double P divided by time by period multiplied by my signal. I don't know how it looks, maybe like this. I do have a set of values. Here are my values. 1, 2, 3. This one last will be space between values. 1 tau or divided by number of values. Is that okay? Here are points. What I need to perform Fourier transform, I need from 0 to time as cosine double P time d time. What's the physical meaning of this mass writing? Maybe your phone can answer. What's the physical meaning of this? You have completed mass course. What's the physical meaning of this integral? Huh? Area of this figure. Area of white figure. I don't know the white line actually, this area. But I have calculated this point. Machine will do it for me. What can I do? I can perform a trick. I can connect points like this, and I can assume what area of all these rectangles is approximately area of my white figure. What's the area of one rectangle? Let's say it's number I. What's an area? It's an value of my signal, yeah? Multiplied by cosine of what? What's an angle here? It's a tricky moment. Since numbering started from 1, but angle here, at this point, angle equals to 0. I minus 1, I need to perform a shift. Totally, there will be, since this point is double P for cosine, for period. One step double P divided by number of steps. And don't forget, what first point is numbered 1, second 2, and until n. So I can substitute wide area with sum of all these column areas. Okay. My integral will be approximately t divided by n, because it's a width of one column, multiplied by sum from 1 to number of columns, each value of my signal, multiplied by cosine I minus 1 double P divided by number of columns. So C1 can be written as P divided by half multiplied 2 divided by period multiplied by period divided by number of points multiplied by sum from 1 to number of points, value of signal number I, cosine I minus 1 double P divided by number of points. This one goes up. Here is approximation. Honestly, I should write approximately for base frequency cosine. If I would like to calculate for 2 omega, if for base frequency cosine travels to P, what will be travel, let's say, for the second? Component 2 omega, it rotates 2 times faster, yeah? Or 4 times? 2 or 4? 2 times faster. Component number 3, 3 times faster. Component number k, k times faster. So cosinus component ck can be written as 2 divided by n. Somewhere I change from 1 to number of points in a period. Value of signal multiplied by cosine of double I minus 1, y double I minus 1. Double P divided by n. And sine component will be 2 divided by number of points. Somewhere I change from 1 to number of points. Value number I of my signal multiplied by sine I minus 1 double P divided by number of points. I just got formulas for what? For discrete time Fourier transform. So if your signal is represented, your periodic signal is represented by table, you can use discrete time Fourier transform to get its Fourier decomposition or get its ideal components. Application of DFT allows me not to calculate Fourier integrals by hand, but do it with the computer. Idea, best, how to say, piece of all this theory is what I can do what? If I have some signal, but this signal should be periodic, apply to some kind of linear network, I have periodic signal, non-harmonic, complex periodic signal applied to linear network. I can do a trick to perform a network analysis. I take my signal, perform a discrete time Fourier transform on it. As a result, I will get DC component and S1 CM set of AC components. This is one DC and this is set of AC component. I should note one thing. There is one serious limitation in discrete time Fourier transform. To perform correctly discrete time Fourier transform, frequency of sampling Fe equals to 1 divided by tau. So frequency of sampling should be at last 2 times higher than max of K divided by period. So frequency of sampling should be at last twice the highest frequency of signal. It's called Nyquist frequency. I will take a closer look, but at this moment it's limits length of the row. I cannot operate with infinite row. To get correct results, I should limit M in the way what max harmonic frequency do not exceed double sampling frequency or Nyquist frequency. It's important. Or I will get kind of disaster. Next step. I will need to solve one DC regime and MAC modes. This block I need to solve my network for one DC regime and one AC. As a result, I will get what? Set of partial regime modes or regimes. As a final, I will get voltage as a function of branch current as a function of time with the help of inverse Fourier transforms. Sounds complicated, but it pays because all the solution can be performed with techniques of classical electrotechnics theory. Without it, you should solve set of differential equation. It's not an easy task, believe me. Okay.